my system. Thanks. I will begin with a word of prayer. Is it bouncing? La, la, la.
Yeah.
All right, great. Dear Father, we thank you for this day, and I just thank you for the students. Just pray you to bless our work today, help us to all understand what we cover, and just to make this time useful, Lord. In your name I pray. Amen. All right, so ideally, I have hours to digest your book and put it into my own words. That didn't happen for me this time. So I'm falling back on my lecture 24 from last time around, which is almost identical content to section 3.3 of Nicholson. So I'd encourage you to read section 3.3 of Nicholson in case I miss something. I may come back and pick up those pieces. I may not. Just, depends. But so today we're going to talk about ideals and factor rings. And, so in the context of groups, what did it take for to define the quotient group? We needed what? We needed a normal subgroup. And normal subgroups are kind of the oddball in terms of terminology. Like every other part of math, pretty much, if you're talking about taking a factor object of something, you talk about the ideals of that object. All right, so in a ring, the thing that you need in order to have a meaningful quotient ring or factor ring is what's called an ideal. So ideals are playing the analog of normal subgroups for us here. So here's the definition of an ideal. I'll just start with that. A subring, A of a ring R is called an ideal if for every R in R and every A in A, both AR, RNA, and RA, RNA. Right. We say A is a proper ideal if what? Yeah. If A is not equal to R. All right, so theorem. Let's see here. So if R was commutative, then we'd only have to check one of these, right? So anyway, theorem, if A is a non-empty subset of a ring, is an ideal if what? 1, we need that if A and B are elements of A, then that implies what? A minus B is an element of A, right? And 2, if A is an element of A and R is an element of the ring, then, well, you're right, implies that AR and RA are in A. So this is a modification of the subring test, right? So the fact that A minus B is an A again gives us that A is a subgroup with respect to the abelian group structure of the ring, right? And then the condition that AR and RA are in A again gives us what a certain professor here likes to call Uberclosure. This is not a technical term, nor should it be mentioned outside the halls of this institution. But I should have paused the recording for a second. But Uberclosure, because it's not just closure of A within A, it's closure of A with things outside of A, right? Like, so. So the proof is pretty much immediate from the subring test and the definition of ideal, this theorem. So can you tell me what are two obvious ideals of any ring? I heard 0, and what else? The ring itself, right? And I should curly bracket 0 are ideals. Only one of those is proper. Only one of them is non-trivial. Let's see here. Another example. Let me call that example 1. Example 2, of course, if we have the ring is the integers, all right, then you can easily prove that NZ forms an ideal. All right, so what's NZ? Yeah.
You get 0 is in A from part 1, but you get 1 is in A.
Is 1 in A? I feel like, because then that would mean that R is in A, which
Right.
R is substitute for A, making A.
Yeah. And here we go. This is the trouble with mixing 2016 abstract algebra with 2017 abstract algebra for me. There is a fix. There is a simple fix. Get out your finger. There we go. Yes, if 1 is in A, you could say bad things happen to us, or you could say good things happen to us. It depends on your viewpoint. But if 1 is in the ideal, that what's that say?
It's not proper.
Well, if 1 was in the ideal, what would that mean? Let's think about that. If 1, this is actually a great question and good discussion for us to have right now, even though I wasn't planning on it. If 1 is an element of A, right, and A has uber closure, then R times 1, right, which is, by the way, equal to R, is an element of A for all R and R. So that pretty much tells you that A is equal to R. Yeah. Which is something we use over and over again in upcoming lectures. If 1 is in the ideal, then it generates the whole ring. You can see that in my example 2 that's about to happen here. If we don't, in NZ, what is NZ? It's n multiples of, the multiples. Let's see here. Nj, such that j is an integer, right? So if you have A and B in here, what's that mean? A is equal to A prime j, and B is equal to B prime. I'm an idiot. Good grief. What does it mean to be an NZ? Sadness. How about A equals to NJ, perhaps? You could call it J sub A if you like, and B is equal to N J sub the J for B, if you like. But J sub A and J sub B are integers, right? So then we can prove that it's an ideal by the ideal test over here, right? So does it pass the ideal test? Well, if we look at A minus B, right, we get N times J sub A minus J sub B, which is clearly in NZ. And how about if you take, and then here's the thing that is kind of foreign to our experience. We take anything in any integer, right? Let R be an element of Z. And if we consider RA, what do we get? we get r times n times j sub a in my current lingo, right? Which is n times r times j sub a. Of course, this is in Z, right? So that's an element of NZ. So yeah, NZ is an ideal of the integers, right? And when can NZ be the integers? When it contains 1, right? When can NZ contain 1? N has to be 1, right? Or what else? Negative 1, yeah. So that's actually kind of a... I am glad you asked me that question now and not like 5 minutes from now, because after 5 minutes it would have been bad. So anyway, thank you for thinking. I like that. Let's see your definition. So thinking is good. We should all think. Definition, let R be a commutative ring with unity. Let R be commutative ring. And of course for us, with 1, right? And let A be an element of the ring, then the principal ideal generated by A is, here it is, bracket A, which is by definition AR such that R is an R. All right. Now, if you like, and this notation is in Nicholson, you could use AR or RA for this just the same, with the understanding that you can multiply a set by an element by pointwise multiplication of the set on either side. Now, this is very bad terminology if we don't have the following theorem, right? What do you think the theorem we should prove next should be? No, well, that's immediate because it's a commutative. We assume commutative here. But this word right here. So theorem, A forms an ideal of R. Again, subject to the terms and condition introduced right here. So if we let, let's say, x and y be an element of the ideal generated by A, what's that mean? That means that there exist R1 and R2 and R. You're like, you could use R sub A and R sub X and R sub Y. I know I could, but oh, fine, I will. You guys happy? You guys happy? There exists R sub X and R sub Y in the ring such that what? X is equal to, apparently, A times R sub X, and Y is equal to A times R sub Y. And quite clearly, if we take the difference or the multiple of one of these by something in the ring, we're back in the ideal again, right? So like X minus Y is A times Rx minus Ry, if you work it out, right? I skipped a step, sorry. I'm not, fine. I'm feeling guilty. Look what you guys have done to me with your glares behind my back. I can feel them. I can feel them. R times X is equal to rar X. But it's commutative, right? So I can move the R over, and so I get a Rex like that. And because we're in a ring, the product of things in the ring is in the ring again, and not to be confused with Rinnigan, that'd be something else. So this is an element of what? this is an element of this guy, right? And this is also an element of that guy, by definition. So there you go. Principal ideal is in fact an ideal. That's good. It would be troubling if we called it an ideal and it wasn't. Am I right? In your heart, you know I'm right. Let's see here. Example 3. So this one's a little bit more fun. If we consider the ring of polynomials with real coefficients, all right, in X, then the ideal X is kind of interesting, right? What's that look like? So it'd be like X times A naught plus A1X plus da 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 plus AN X to the n, something like that, right? Let me call this stupid thing f of x because I'm tired of it. Can you put it into words? What is this ideal? So you said it's all polynomials with root 0. That's not a bad thing from our previous experience, but we don't necessarily think of polynomials as functions in abstract algebra. So, I mean, it's not wrong. It's not wrong. But another way to say that, of course, would be polynomials with what? No constant term, right? And when I say no, I mean what? No non-trivial, right? You're like, the constant term is there, it's just 0. Well, okay. If you're going to be like that, we can't have a conversation. It's here. Example 4. Here we have the ring of polynomials in x and y. So this would be polynomials, so this has things like x squared, xy, x squared y, x squared y squared. It's got all kinds of stuff in there. So like a typical thing in here is what? I don't think I've talked about this before. Typical element looks like this. It's the sum I and j equals 0 to infinity of aij x to the I, y to the j, finitely many aij not equal to 0. Since this is the first time this example is entering the scene, I should mention to you we could formally introduce this as this as well. We could say, well, that's polynomials in x, in y. So the polynomials in x being a ring, you could use those as coefficients for polynomials in y. And that's naturally the way to construct polynomials in x and y. Now, you say, well, we haven't formally constructed polynomials in anything yet, so you're, flag on the play. Well, fine, that's true, we haven't done that yet, but you can, and we will eventually. And when we do, this is how we will formally build polynomials in two variables, just like that. I might have in linear, but not everyone's had linear with me. Let's see here. And I'm quite certain that if you didn't have my linear, it wasn't done. Let's see here. So in this context, what would x look like? It's different now, isn't it? So now you're looking at, this has what? Polynomials. Well, let me just mention some typical things. You could have like x, and then you could have 1 plus y plus xy, et cetera, et cetera. That's something in here, right? Again, you still have no what? You have no constant, yeah. It's polynomials which have 0 constant term and no terms with just y also, right? So like y squared, these are not elements of this, right? Okay. You could also look at this thing, right? That would also be an ideal in here that's kind of interesting. So lots of interesting examples to play with in this ring. I just thrown it out there as it's a good thing to look for examples in, is my point. All right. If you can do it for one, you can do it for more. So definition, I don't want to do it there. So we can also look at the ideal generated by more than one thing. So definition, if you have A1, A2, AN, this is the set of all A1R1 plus A2R2 plus plus ANRN, such that R1, R2, Rn is in the ring. This is the principal ideal generated by A1 through AN. Excuse me, it's not principal. This is the ideal generated by R1 through Rn. It's not principal. Ideal. Unless n happens to be what? If n is 1, if it's just one thing, then it's called a principal ideal, okay? Not all ideals are principal. Example. Let's see here. 5. Is this working today? It's working. I tried to use it yesterday. But if you look at zx, so polynomials over x, this is a commutative unital ring, right? Here again, I'm assuming that this is commutative, okay? Just like we did for the previous definition. There's a theorem that follows, which is what? What do you think the theorem I should have written here? Yeah. That was a homework in 2016. I don't know if it's a homework this semester, I can't remember, but it's a simple homework. It's a nice one. If we look at this ring, all right, we look at the ring of integer coefficient polynomials in x, you can actually show that the ideal x comma 2, all right, is an interesting ideal. This is things of the form what? Basically, this has things like x times h of x, right, plus 2 times j of x, where h of x and j of x are in z of x, right? I mean, polynomials with integer coefficients. Anyway, I'm sorry, that was not the example of, I don't think that was the example of an ideal which is not principal. I think that's just an interesting example. So let me help us out here a little bit. I've got some pictures, and the proof that I was about to go over would take me 20 minutes of writing, and it would not be that interesting to watch me write either. It's better for us to look at this. I'm so happy this is working. I thought this wasn't working. It wasn't working yesterday, which is why we, with the computer. Well, maybe you don't know. If you have questions about that group project, which is not a group project. Yes. Yes, Sam.
Is that ideal just equal to
I don't. No, this is not just ZX.
I thought it was R.
It's not just ZX because there's no way I can get. I only have even constant terms here. That's the thing that's limiting. So you don't get everything. Yeah. All right, so we just got to example 12 in my notes, actually. That was this one. My next example is just functions. If we look at the product and difference of differentiable functions, it's once more differentiable. It's not the case that the product of any function in all of functions from R to R is differentiable because, let's see here. This is a function, g of x equals absolute value x defines a function, and yet this times that is not everywhere differentiable. Set of differentiable functions is a subring, but not an ideal. I mean, okay, fine, we can read this, whatever. Sorry, I should have skipped that. This is the main point. Okay, here we go. So, if we have R as a ring, and A is a subring of R, we can define a set of cosets, R mod A, to be, so we look at R plus A, the additive cosets, all right? And this is going to be the factor ring, all right? The operations on the factor ring are addition and multiplication in this way. And so in this factor ring, A behaves like 0, right? It's an additive coset. So like A is like 0 here. In contrast, when we're dealing with quotient groups, the thing where like the H was behaving in some sense more like 1 for a lot of our multiplicative examples, right? But we also have additive examples where the H behaves like 0. It kind of depends on the context. But here, the context is that we're taking this quotient with respect to, in some sense, the group structure here, which is an additive abelian group for the ring, right? So these are additive cosets. But we can define a multiplication on them. And in so doing, that gives us the structure of a ring because we have an addition and we have multiplication. But this only makes sense if A is an ideal, all right? So here's the details. So first of all, suppose you have two different representatives for S plus A. So you've got S plus A is S prime plus A, and you've got T plus A is equal to T prime plus A. We should like that these operations don't care about the choice of representatives, right? So if you look at this, of course I have S minus S prime and T minus T prime are in A. So I call T minus T prime A, and I call S prime minus S prime little b, little a. And if you look at the product of S and T, it's equal to, see I solve this for T. T is A plus T prime. Here S is B plus S prime. So S times T is that times that, which when you multiply it out, you get this. But the thing is, if you look at that, remember that A is an A, right? And B is an A. So AB is an A again. And S prime A, well, that's in A again because A is an ideal. You see, the ideal structure, you need it on both sides because you need this to get absorbed into the ring, in the ideal rather, and you need this to get absorbed into the ideal. You need both of those things in order that this whole thing right here is in A again, which means that S prime, T prime, and ST are representing the same coset, which is to say that this multiplication up here is well defined. And the proof that the addition is well defined, well, we already did that. That's just the additive factor group construction. So the fact that A is a subgroup and the addition is abelian suffices to prove that this is well defined. But I think I have the proof right here anyway. So there it is. It should say subrung. You're right. Yeah, you have to delete that I from the record here. Keep in mind these notes are from the other definition of ring. I'm so sorry. Sadness. Yes? The what?
The ring is still abelian, right?
The ring is still abelian.
You still assume that the ring R is abelian.
I do not believe we're assuming that this ring is commutative, no. No.
How do you form ideal in a non-commutative ring?
What's that? How do you form an ideal? Well, that's the thing is the definition I erased over here. We assume that both AR, the left and right multiples of the ring with the ideal are swallowed back into the ideal. If we're working in a commutative context, we would only need that like AR was in A again, but we assume that AR and RA are in A again. So the setup for the factor for an ideal is in, it allows for the non-commutative ring case, yeah.
The definition of ideal didn't include commutative, it was only
Right.
definitions of the generated ideals.
It's annoying, but you're right. I mean, we've been trying to have our cake and not commute it too or something. I don't know. But yes, this definition and the principal ideal definition both assume commutative rings, but the definition of factor ring does not, which is important because we want to look at matrix examples which are non-commutative. So it's not just needless generalization. We have examples that we need to include, and yeah.
Principal ideal definition in Nicholson says that it's just in the center. Is that good too? I mean, obviously if it's commutative in the center is the ring, but it's a little different.
This is our definition of principal, so we may need to prove a theorem that it's the same as what Nicholson says. But for my, I mean, this is what I told you guys, so you can use it. Yeah. This is a very convenient definition, if nothing else. So more about that later. But where are we? So great, the operations are well defined, but that's not enough. They also have to satisfy the ring axioms, right? This is the factor ring. It's not part of some subring which is already existing. We actually have to check the axioms, which are what? Zero's in there, the addition's commutative, the addition's associative, there's a negative for everything with respect to addition. We have distributivity on the left, distributivity on the right, and also, for us, I guess that there's a 1 in the ring, all right? But you won't find the 1 in this proof, of course, because this is, but we'll fix that. That's not a big deal. So like here's the, what is this? What's going on here? Which one am I checking? Associativity. Am I missing a plus?
Well, it says associative and distributive properties. Is that just
What am I doing here?
yeah, it looks like associativity and multiplication.
Oh, right. I almost forgot about that one. That's right. We also need associativity of the multiplication. I'm so sorry. I forgot about that. I didn't list that just now. But anyway, you can understand what goes on here. We combine ST first, right? And then we combine R with ST. But then, it's every one of these stupid properties is the same thing every time. The reason that you get the corresponding property for the factor ring is because once you get down to the level of representatives, you can use the corresponding property for the ring, which you're forming the quotient of, right? Like this is that because that's one of the axioms for a ring overall. Is we have this associativity of elements in R. And then you just undo it and get back to the other multiplication. And I think, oh yeah, I'm sorry, I just have trouble seeing the parentheses. I'm too close to it. But these would be bigger if it'd be better. It'd be better if these were bigger. These should be bigger. I think it's a tech error. Here's the actual distributive property. So this times that, so we can add the S and the T first by definition, and then multiplication, we multiply representatives like that. This is going from here to here, that's the axiom for the ring, and then you just undo it, which is, this is that plus that, which again by definition is this, which is just distributive property. All right. So every, we do have a factor ring. We have a way to build a new ring given a ring and an ideal, right? But there's one thing missing. So let's add this since our rings are commutative. What would we like? We also need a 1. What's 1? What's 1 in our what am I dealing with here? R mod A, right? What do you guys think? What should function as the unity? What should be the 1 in here? Sam conjectures that it is equal to 1 plus A. That seems like a very good choice, because if we take 1 plus A, right, and we multiply it by anything, right, we get 1 times R plus A, which is R plus A. So there you have it. In fact, yes, the representative, the coset corresponding to 1, right? The coset with representative 1 is the multiplicative identity of the factor ring. And what happens if 1 is in the ideal? Then it's the stupid ring. Yeah, it's the stupid ring. Then you're looking at R mod R, which is just 0, where 0 is equal to 1, right? We're back to that again. Now, here is also a useful discussion about what happens if A is not an ideal. And this paragraph gives us the proof that if A is not an ideal, then you cannot do this, all right? It's not just, oh, if it's an ideal, it works, and if it's not an ideal, it sometimes works. No, if it's not an ideal, it fails. You cannot form the quotient ring as we have. Here's the proof. So suppose it's not an ideal. First of all, if A is not a subring, then that means that R mod A is not an additive group because of the group theory we've already done. The only way we can form a factor group with respect to the abelian group structure here is to have a subgroup, right? So that's the first thing. If it's not a subring, right, game over. So suppose it is a subring, but it's not an ideal. Then we have an additive structure on the set of cosets, but apparently there exists R in A such that AR or RA is not in A, right? So suppose that AR is not in A. If AR is not in A, well, we can check this out. So A plus A is 0 plus A, right? These are equal because if A is in A, then let's see here. R plus A, that's also an element of this coset, great. If we look at the product, we get A plus A times R plus A is AR plus A, right?
Should R be in R?
Yeah, R is in R. So we have 0 plus A times R plus A is that's A, and yet we also have that it's AR plus A, but they can't both be, A is not equal to AR plus A because AR is not an element of A. So that's a contradiction. And you can give a very similar argument for the opposite case. So that shows you that, in fact, you cannot form the factor ring unless you have an ideal. Now, here's the real reason I wanted to have this out today. I wanted to show you examples. These examples take me forever to write out, but we can all appreciate them if I project them. Right, so here they are. So this one, of course, Z and 3Z, well, there's your additive Cayley table, there's your multiplicative Cayley table, but that's a factor ring, right? Because 3Z is an ideal. You know, maybe you didn't think about it this way yet, but we've been dealing with factor rings since about day 2. Just now we've actually constructed them. All right. This example is a little bit more out there. If we look at 2 by 2 integer matrices, all right, and consider the ideal of even entried 2 by 2 matrices. Think about it. If you take the difference of even entried matrices, you get a matrix with even entries, right? And if you take any matrix and matrix of integer matrix and you multiply it by an even integer matrix, if you think about how matrix multiplication works, you always have one of the numbers from each entry of the even matrix multiplying everything, so you have sum of even things. It's still an even. It's easy to check. It's actually in. Well, look. I mean, this is even better than what I was saying, right? If x is an even, that's 2x prime, so that's that. If 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 z is in the ideal, then that's, I'm sorry, I can't do math. What side am I on? Anyway, let me move along. It is an ideal. I think I should check. I should really check both. It seems like here I should actually check both, right? You know, I should check that RA and AR are both, capital, lowercase, RA and AR are both elements of A again, right? I mean, because here the multiplication actually is in principle non-commutative. So, yeah. Anyway, getting to the point here, these are the representatives of the factor group. You've got, A, which is serving as 0. You got this guy, that guy, that guy. What is that? I thought it was my laser, but it's not. It's you see that every once in a while? There's something up here. Must be a bug. Anyway, it's fairly clear that this is just, there's 16 things, right? You've got 4 binary digits, and they're ranging from 0 to 1, and 2 to the 4th, 16 distinct cosets. Now, that one's fine, but here's this one. This one is interesting. The Gaussian integers, all right? Gaussian integers, we can visualize this z adjoint I is a lattice. You can look at it as a lattice of points in the complex plane. I have some dots down here, right? And I can look at the principal ideal, the ideal generated by 2 minus I. Okay? So you want to understand what cosets look like. Cosets would have the form a plus bi plus 2 minus I, right? But if you think about that, how does it work? The idea is essentially that the thing in A serves as 0 in the factor group, right? So if I'm generating the principal ideal by 2 minus I, that means as far as representatives go, 2 is equal to I. This is how to look at it. And so if you sort through that, we have representatives 0, 1, 2, 2 plus I, and 1 plus I. These are the distinct cosets with respect to that ideal. Let's see here if I can show you a picture here. So let's see here. The ideal I'm looking at was 2 minus I, right? So I'm saying that 0 and Sorry, I'm very confused all of a sudden. I think I'm doing 2 plus I here. What's that again?
Multiply I by 2 minus I, you get 1 plus 2I, which is that upper point tensor.
Say that again, Sam. Just exactly what you just said. What do you say?
So take 2 minus I, multiply by
2 minus I times I.
you get I plus, 1 plus 2I.
Oh, okay. Yeah, it'll mess with me. Okay, great. That is important because that's actually how I'm thinking geometrically. So if this is an element of what? This is in the ring, right? So it's a principal ideal, which means that this is also an element of, well, by definition, right? So if I take a point and I add, whoa, not good. I just kind of just lasered myself. Let's hear. So if you take 0 plus 2 plus words, 0 plus 1 plus 2I, then we're in the same coset, right? You see what I'm saying? If I have, let's say, A plus IB, right, plus, this coset, and then that is equal to A plus IB, parentheses, plus 1 plus 2I. Now, you could pick on anything you like. So I think that's how I'm seeing that this 0 is in the same coset as 1 plus 2I there, right? Yeah. So I've got some wrong thought that I can't get out of my head, so I just got to stop. The point is, this is a picture of the factor group of the Gaussian integers by the principal ideal 2 minus I. And after you sit and think about it, draw this picture, and come to terms with the fact that there are 5 of them, this is sort of a geometric picture of what that is. And so there are 5 cosets, right, in the factor ring. What is it? What's that? It's oh yeah, exactly. They are in the. This is so I picked this square. Like if you take that square, if you take that and shift it around, any one of those regions that you cover, you'll get a representative from each one of the classes, right? In other words, a blue dot, a green dot, a pink dot, a yellow dot, a red dot, and these 4 are the same. The corners here are all part of the same coset, right? How do I get from here to here?
Once you have 2 minus I and 1 plus 2I, you just add multiples of them together.
So here I add 2 and subtract I, right? And this is subtracting, yeah. But it's also kind of neat because if you just look at these down here, right, -1, 0. If you could keep going, we'd have a yellow dot over here, right? So that actually is, those are representatives, if you will, of the factor group here. My larger point to you is, what is this? I mean, up to isomorphism. If we had some concept of isomorphism here, we will soon. What is this?
Z5.
It's Z5. Thank you. All right. We'll come back to that later. So next time, I will talk more properly about prime ideals and maximal ideals. A prime ideal is one for which if you have A and B in the ideal, it implies either A is in the ideal or B is in the ideal. A maximal ideal is one that's, well, maximal. So if it's a maximal ideal, if you have B between the maximal ideal and the ring, that means that either B is A or B is the ring. So the maximal ideal is sort of the largest ideal which you can find in the ring, except for the ring itself, right? Yeah.
Under that definition, when the ring comes to, oh, never mind.
Now, not surprisingly, if we look at PZ, where P is a prime, that's a prime ideal. This picture is good while I've got it out. We get the most out of this here. If we look at Z36, in Z36, 2 and 3 are maximal ideals, right? If we look at 6, under 6, 12, and 18 are maximal ideals of 6, right? By the way, it's not an accident. Z36 mod 230, Z36, this is isomorphic to Z2. And Z36 mod 3 thrice Z36 is isomorphic to Z3. It's not an accident that the quotient by the maximal ideals here are fields. This is, in fact, a theorem that we'll prove next time. If we have a maximal ideal, all right, here's the big theorems from next time. If we have a commutative ring with unity, and if A is an ideal, the quotient ring R mod A is an integral domain if and only if A is prime. This is the important thing about prime ideals. Quotients by prime ideals give us integral domains, and quotients by maximal ideals give us fields, right? So this is very, very useful as we're studying quotient rings. It gives us a way of understanding when we form one of these factor rings, do we have something that's an integral domain or do we have something that's a field? You know, how can you detect the nature of your factor ring by just looking at the structure of the ideal, and that's it. So anyway, sorry I didn't get more done today. I think I'm behind. You'll forgive me. Or not, I don't know.